welcome to the summer school. We are very happy to have Yael Kalai as our first speaker. Yael is a faculty at MIT, also has a position at Microsoft Research. Yael has done a lot of exciting work in cryptography, complexity, privacy. She's also recipient of an outstanding master's thesis, outstanding graduate thesis. She's also an invited speaker at the International Congress of Mathematicians, and she's going to tell us about the magic of cryptography.
Thank you so much, Mutur. Thank you so much, guys, for joining. So before I start, though, a few comments. So first of all, I can't see hands and everything here on the screen because I'm in full, the mode I'm in, I can't see anything. Just whenever you have something to say, just unmute yourself and stop me. You don't need to, the more interactive it is, the better. My goal is actually not to teach you as much material as I can about cryptography, but rather to kind of engage in a conversation so that you'll understand kind of what cryptographic thinking is like, okay? Give you concepts as opposed to a lot of material. So I hope that, it should be fun and interactive. So again, just unmute yourself and jump right in. The other thing I wanted to say is I had COVID like 8 days ago, so I'm still coughing a little bit. Don't worry, it's not contagious via Zoom. And also I shouldn't be contagious anymore anyway, but I may be coughing throughout, so sorry about that. Okay, so with that, let's start. First I want to introduce the two great TAs here, so Huang and Sherry. And
sorry, I'm having trouble hearing. Can you say that again?
Oh my God, sorry, that was Alexa. Okay, so they will help you with the homeworks and so on and understanding material later on. Okay, so let's start. So as I said, my goal for the two lectures that I have here is to kind of show you kind of the magic of cryptography, how magical and wonderful cryptography is. And my first lecture today is going to be about kind of how you can generate randomness out of thin air and why this is kind of the bread and butter and what enables us to do cryptography. So that's going to be today. That's the first magic. And the second magic that we'll see on Wednesday, or tomorrow, sorry, is the concept of zero knowledge proof, which is also a very kind of a magical concept that we'll see tomorrow. Okay, but let's start kind of with the most basic kind of term of cryptography, which is that of encryption. Okay, so what's an encryption scheme? In an encryption scheme, the goal is just to be able to send secret messages on a public channel between two parties. So Alice and Bob, they want to send a message. Any eavesdropper can see, and they wanted to do it while the person who's eavesdropping cannot understand the message. Okay, so cannot learn M. And in order to do that, they share some secret key K. So there's some secret key, like a random key, shared between Alice and Bob, and we assume that they're the only people who know the key. Nobody else. So the eavesdroppers do not know the key. And instead of sending the message M in the clear, just like that, so the eavesdropper can learn it, what Alice will do is she will send an encryption of M. This is a function of her key, of the key they share, and the message M. Okay, and we denote this encryption by C for ciphertext. So instead of sending M, she will send C, a ciphertext, which is a function of M and the shared key she shares with Bob. Okay, and what we want is the notion of confidentiality, meaning that an eavesdropper, often referred to Eve, he only sees C. He does not know K, he only sees C, and we want to ensure that he does not learn the message M. Okay, so that's kind of the most basic primitive in cryptography. Let me say this a bit more formally, so we'll have kind of the language. So what do we want? So we have two parties, Alice and Bob. They generate a shared random secret key K. So Alice and Bob both know K. We have an encryption algorithm denoted by E, where it allows these parties to encrypt messages to each other. E is a function of this joint of the shared random secret key K and the message they want to send. you get back a ciphertext C. That's how you encrypt. And then Bob, who knows his key K, he gets a ciphertext C to decrypt C. What he does is he has some function D for decryption that he applies to his secret K in the ciphertext C. Okay, and recall the ciphertext C is nothing but an encryption of the key K in the message M. Okay, and what we want from an encryption scheme is correctness. Namely, when you indeed decrypt a ciphertext that's an encryption of M, you should get back M. Okay, and so that's correctness. And for secrecy, we want to know that an eavesdropper who does not know the secret key, he cannot decipher, so he cannot learn the message M from the ciphertext. And that's the basic kind of idea. So we generate a random key, we have an encryption algorithm, and we have a decryption algorithm. We want correctness. If you decrypt an encryption of M, you should get M, assuming you encrypt and decrypt with the same key. And we want secrecy that, given if you do not know the key and you see the ciphertext, you do not learn the message. Okay, any questions? Again, feel free to unmute yourself. I love questions.
How do they both know the key?
Great question. I love that question. So the question is, how do they both agree on, how do they know the key? And actually, that's a wonderful question. That's indeed a very hard problem. How do they share a key? One way they can share a key is, they get together, they whisper to one another, and kind of that nobody hears, and then they go back, they agree on this key kind of secretly, then they go back and they have their key. Actually, this, so the way it was used, like by Army, this kind of symmetric encryption, this is called symmetric encryption because they share a key, they share kind of, they both share the same key, or secret key encryption also it's called. And it's been used like all throughout, I think it's still used in Army and stuff like that. It's been used throughout World War II. And the way it's been done then is actually, before you go to war, the generals sit in the main base, they get a huge key, it's kind of in a briefcase, all the bits, the keys usually are bits 0 and 0 and 0 and 0 and 0, many, many bits. They put in a briefcase, kind of rolled, in a briefcase. They attach it with kind of handcuffs so it won't be able, people can't steal it, to the generals, and they walk with that, to where they need to be, and then they open. So that's actually how it was done, like very low-tech kind of way. Today, we still use encryption, like over the internet and so on. Often we don't use this type of secret key encryption. We use what's called public key encryption. And actually, one of the homework assignments is you're going to try to do a small part of that on your own. So sharing a key is hard. How do you share a key? Actually, you'll get a homework assignment on that. Okay, so we'll get to that at the end of the lecture when I'll go over the homework quickly, and we'll talk about that. But for now, just assume they do share a key. Somehow they got together, they whispered it to one another, they met before, they put the big secret key in a briefcase, they went their own way, and now they share a key. Okay, did that answer your question?
Yeah, thank you so much.
Great. Any other questions?
Yeah, can you
Yes.
hear me? Yeah, I wonder whether this might be a little bit, okay, so I have an idea like about sharing the keys. I mean, there's also a question, does the people share the key in a way like the communication complexity, like it's like a protocol, like they're each people send each other bits or something like this, and finally like both people, like both guy like know somehow the bit string or a sequence of bits, and that is, I don't know. I wonder whether this is the case or this is related to the case that, of sharing the key.
Right. So in this, for now, I kind of assume that it's already shared. So somehow Alice and Bob agreed. I'm kind of not telling you how they actually do agree on it. Indeed, at the end of the day, you're right, it's a protocol. There's going to be some kind of key agreement protocol between Alice and Bob. And how to do this protocol over a public channel is actually not trivial. And you'll see that in the homework, how to do that. But here for now, I just assume that that's already done. Okay, they do share a key.
Okay,
They managed to share a secret key that Eve does not know, and we're starting from here. But you're right that there's a point of in what, so either they get together, but in real life, actually, the way they share a key is via some communication protocol. And we'll talk about, you'll see kind of in the homework how to share a key via a protocol for that.
Thank you.
That's going to be one of the homework assignments. Okay, great. So let me give you an example of a very, very simple encryption scheme that was actually used throughout the years. It's been the main scheme that was used during World War II, and that's called the one-time pad. Okay, so what's the one-time pad? It's very simple. Here's the idea. First, what is the key? The key is just a random bit stream. Okay, 0, 1, 1, 0, 0, whatever, just a random bit stream. That's the key. So we somehow agree on a secret key K, completely random string, bits. Now, suppose I want to encrypt a message M with a key K. So first, we usually think of our messages, not always actually, but for now, we think of our messages as bits. Okay, so the message is just 0, 1, 1, 0, 0, 0. Just think of it as a, so whatever your message is in English or whatever, you first convert it to some bit string. Okay, and I'm not going to talk about this conversion. These are kind of their standard ways to convert any kind of human language to bits of 0, 1, 0, 1. Okay, so now let's assume that the message you want to send is already just bits. Okay, so in this case, what is the, you have a key K of bits, you have a message M of bits. What is the ciphertext? The ciphertext will just be the XOR. And what I mean by XOR, I mean bit by bit XOR. So 0 XOR with 1, XOR is just addition mod 2. Okay, so 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 mod 2 is 0, and so on and so forth. Okay, so you just XOR the key and the message kind of bit by bit. That's the ciphertext. Okay, let's see. How do we decrypt?
Sorry. In this case, do K and M have to be the same length strings?
Great. Great. Yes, the question was, do K and M need to be the same length? Well, I'm used to repeating the questions for recording, but now you can all hear actually. The answer is yes. We assume here for this encryption scheme, the key size and the message size, so the key length and message length are equal, same length. And that's why you can indeed XOR bit by bit. Otherwise, it doesn't make sense. Yes. Or the key can be bigger, but it needs to be at least to have enough room to XOR, you know, to kind of pad the message. It's called a one-time pad because you can think of a K as a pad. It kind of pads each bit, you know, with a bit of the key. Okay, so that's the encryption. You have great questions, so thanks, keep them going. Okay, so that's how you encrypt. Any idea how to decrypt?
To decrypt, you do M XOR C. And sorry, it's an accident. I'm going to say K XOR C.
Exactly, fantastic, perfect. How do you decrypt? You just take the key, you take the ciphertext, and you XOR them to get the message. Why is that a good decryption? Because what is C? Remember, the ciphertext is just the key XOR with the message. Again, this is what I mean here is bit by bit, okay? It's a kind of a sloppy way to denote. Usually we think of XOR as just one bit and XOR one bit, but you can just think of it as strings and XOR bit by bit. So this is what this notation means. But so what is K? XOR the ciphertext, which is K XOR M. This by transitivity is just K XOR K XOR M, but K XOR K is 0. Because when you 0 plus 0 is 0 and 1 plus 1, mod 2 is also 0. So you get 0 XOR M, which is M. So you got back your message. Done. Good. So you got the correctness. We can encrypt. We can decrypt correctly. That's great. How about security? Okay. So now this is kind of the first time where I want you kind of to think as a cryptographer. And how would we so the question is secure. And to answer this question, the first thing we need to do is to understand what do we mean by secure? What does security mean here? What do you want from security? So actually, before we answer, is it secure? Let's first define what is security. So does anyone have any idea? How would you define security? Let's give me kind of, let's try.
I would guess it's either related to you either. So if I'm Eve and I were to get a encrypted string, I would, the goal would be that either I can't decrypt it, or I would think of this from like a complexity standpoint where like I can't decrypt it efficiently.
Okay, great. Wonderful. So good, right? You can't decrypt it. You're right. So one way to say it, you can say, well, you know, let me state it a bit more kind of a little different. They say, you know, here's an attempt. Eve cannot learn anything about the messenger. So, okay, what you said you cannot decrypt. Look, it may be very hard to decrypt, but that's not actually enough. Why? Because I mean, that you need that for sure. If you can decrypt, if you can always decrypt, that's a bad scheme. That's no question. But what if you can't decrypt completely, but you can learn the first half of the message? That's not good. I want to hide all the message, not just, you know, it's not enough for me to say you can't learn all of it. You want to say you can't learn none of it, in a sense. So maybe I should say, you know, you can't learn anything. So one extreme is you can't learn everything. That's a bit weak. Maybe I should say you can't learn anything. But that's too strong. First of all, you know, you do need to learn the message length. And the reason why you need to learn the message length is because if you, let's say in one case I want to encrypt 1 bit, in another case I want to encrypt a gigabyte. If I encrypt a gigabyte, the ciphertext needs to be at least a gigabit long because, you know, it has to have the information about the message so it can be retrieved later. But I don't want a 1-bit message to be length of a gigabyte. That would be totally inefficient. So I should at least kind of, the encryption scheme, the ciphertext does leak the length. Okay, so maybe I should say, I don't know, Eve doesn't learn anything except for the length. What about that? Does that seem like a good definition? So no, what do I have here? I'm saying Eve cannot learn anything about the message except for its length.
I feel like the length could still matter.
Okay, so you're right. So let me point, okay, that's a very good point. You're saying, look, length can be important, and it can. And usually the way, in today's schemes, actually, the length is always leaked. But if you don't want your length to be leaked, what you do is you pad. So let's say, you were sent a message, and you know that the attacker, now you want to answer. And you know that the attacker, like either you send a very like no answer, or it's yes and why. So you don't want, if you send just 1 bit, that verse will know, oh, it's a no. Because if it was a yes, he knows it's yes and why in explanation. So by just seeing 1 bit, he knows that the answer is no. You want to hide that. Usually the way you hide it is not in the encryption. The way you do it is you write in your message, my answer is no. But now I'm blah, blah, blahing because I don't want the adversary to know that I'm just sending 1 bit. So just ignore this part. I'm just going to send zeros. So in other words, if you want to hide the length of your message, you'll pad it. You'll make it longer, just kind of to kind of deceive the adversary. Okay, so that's not done in the encryption itself. It's done in a padding level. But as I said, you have to kind of leak the message length in some sense, because I mean, you're not going to make it a gigabyte. You're not going to make it infinite. So by making it at most, by saying, okay, it's going to be at most this size, you're leaking that amount of information. You're leaking that it's at most that size. But you can pad. So we deal with it in kind of a padding level. But that's a very good, you guys are great. You're not letting me kind of hide anything under the table, or, so that's wonderful. Okay, so let's go back to this attempt. Is it a good one? And actually, I want to say this attempt, okay, so let's say establish, okay, we're okay with learning the length. And if we really want to hide the length, we'll pad it. Okay, so let's put the length aside. You're like, look, great, you don't learn anything. What more do you want? But I want to argue that this is too strong. What do you mean you don't learn anything? Maybe you know things about the message. So maybe the adversary, okay, what do I mean? Let me actually say, what do I mean you don't learn anything? You can say, don't learn anything, meaning that the eavesdropper, he can predict kind of any bit of the message is probably better than half. That means he doesn't learn anything, right? You learn nothing. You can't predict. Is this bit 0, this bit 0, this? You don't know. But why? But maybe actually Eve can predict. Maybe Eve knows that, every time I send a message, I start with Dear Joe. So she knows that the first, she can predict that the first bits of the message correspond to Dear Joe. And actually, this is not like an esoteric kind of example. Actually, the way we encode messages, there are, like, we know, for example, if you encode it using ASCII, then you know that the higher order bit is 0. So you can predict that bit is going to be 0. So the way we encode the bit, actually, there's information. It's not and maybe, moreover, maybe, as I said, the eavesdropper knows some information. He knows headers of messages, for example. Okay, so the message is real. Not everything is hidden from the eavesdropper. The eavesdropper often does know some information about the message sent. Maybe he does know the secret part of the message, but there's a lot of information that he does know about the message. Okay, so that's not good. You can't say Eve doesn't know anything about the message. What we really want is to say Eve doesn't learn more by seeing the ciphertext. So Eve may know information about the message to be sent, but he doesn't learn the ciphertext itself doesn't give him more information beyond the length. Okay, so from now on, I'm just thinking of fixed length messages. From now throughout the rest of the lecture today, let's just think, the messages are n bits. Each message is n bit, that's it. That's known. Okay, so I don't need to say every time except for the length and for the length. So we fix the n bit messages. N can be anything, it can be 1 bit message. Every time you encrypt for just 1 bit, it can be 128 bits, it can be anything you want. Fix kind of in your head a number, and now that's the message length. So really what we want to say is that Eve learned nothing about the message she doesn't learn more by seeing the ciphertext. Whatever she knew before, that's what she knows now, but no more. Any questions?
Sorry, I have a question. What if Eve doesn't learn anything more about M by seeing C, and she doesn't learn anything more about some other message M prime by seeing its ciphertext C prime? And when she sees both C and C prime,
she learns all of a sudden. Yes, great. This is a great question. Actually, for now, okay, so let's keep it in mind. You're right, but for now, okay, you're right. Actually, you're right. We'll get back to your point in a second. What this really promises you, what I write here, what I promise you, is only what's called a one-time security. Okay, so let's say you see one ciphertext, not two, one. We're using the scheme once. So you're totally right, you're totally onto it. But for now, I want to say, if I use my encryption once, then I want to argue that this is a good definition. Let me say it a little more formally now, and I'm going to use some notation that I'm going to explain here. So I want to say, this is secure for one time, not many. You're totally right. You've gotten to a very good point. But for one time, you want to say that for any two messages of equal length, if you look at the distribution, so now take any messages, 000 and 111, 101 and 011, whatever two messages you have in mind, look at the encryption, choose a random key, and look at the encryption of that key with M. This is some distribution, right? It's like because K is a random variable, M is fixed. But now, this here is a distribution where a random key is chosen, and what's output output is the encryption of K with M. Let's look at another distribution where again, a random key is chosen, but now we encrypt K and M prime. What I want is that these two distributions are identical. So this here is it's a notion of equivalence as opposed to equality. This is just to say that I want them to be equivalent as distributions. Okay, this is just to emphasize that we're dealing here with distributions as opposed to numbers. So I don't mean take a fixed K and look at this number and look at this number, they're the same. Actually, they won't be the same for a fixed K. But if you look at a random K and look at this distribution, and take a random K and look at this distribution, you want to say, look, you don't learn anything. So what does the Eve see? What Eve sees is a sample, either from this distribution or from this distribution. Because from Eve's perspective, assuming we do it once, Alice and Bob tossed coins to get K somehow, and now she sees the ciphertext. So she really sees either an kind of sample from this distribution or a sample from this distribution. And if these distributions are identical, she learned no more about, even if she knew M and M prime completely. Okay, let's say Alan, like the adversary, actually she knows a lot about N and M prime, maybe everything except for the last kind of bit. And that's what she wants to learn, the last bit. Well, it doesn't matter, even if she knows everything. The point is that for any fixed M and M prime, if you look at this distribution, you sample a random key and you look at the outcome, this is the same. So she learned nothing. What she learned, the ciphertext, actually doesn't depend on M and M prime if you don't know the key. Of course, if you know the key, it's a different story. So if you add key here, then of course, you lose the equivalent. But I'm not adding a key. And without the key, of course, if you add the key, then you know they're not the same because you can decrypt. But without the key, I want to say she didn't learn anything. Okay, so for one time, are you happy with this definition?
Yeah, something.
Sure.
Doesn't that definition of security greatly depend on the prior that Eve has on like the information? Because especially if we consider like one-time pad, I feel like depending on the information that Eve has, we couldn't really come up with a secure mechanism. So I feel like we should know what Eve knows to be able to do that, or is that not true?
Okay, so great question. I want to argue that because I'm quantifying here for every M and M prime, from my perspective, Eve can know anything she wants. Even she can know the entire M and M prime. But what I am assuming, and that's crucial, that she knows nothing about the key. So the key, it's completely secret from her. But the M's, she can know everything about, because I'm saying, you know what, even if you know M and M prime completely, still, this and this have the same distribution. From your perspective, let's say I'm telling you, look, either M or M prime is encrypted. Tell me which one. You don't know, because in both cases, I'm giving you a sample from the same distribution.
Just out of curiosity, will this be similar to hashing, or is this completely different?
It's completely different to hashing. The reason it's completely different is hashing, all it does is it takes like a string and it hashes it down and makes it, but you can't undo. Usually hashing, in many cases, it also shrinks in many applications. Here, I want to be able to decode. I need to decrypt. And that's something that hashing does not allow you to do. Let me just say, though, many encryption schemes use hashing as a building block, but that's not, it's not enough. Okay, so the difference between hashing is hashing often just compresses or hides things, but you cannot decrypt. And an encryption scheme offers you the ability to decrypt, and that's very important.
Yeah, I have something to. I have some idea about this. I think like I personally think that this attempt on the screen is not like, it's a little bit weird for me, because I think like it will be very hard to make two distribution. Can you hear me?
Yeah.
I think it will be very hard to make two distribution completely equivalent. Like this is sort of like magical. Like what I'm thinking is that maybe we can make another distribution which is just very similar. Like they have, very small differences.
Great. So what you're saying, let me repeat, and you're completely right. You say, wait, why would you really require it to be the same distribution? That's very strong. Like it seems like very hard to get. Isn't it enough to assume that there may not be exactly the same, but as long as from Eve's perspective, she can't tell the difference, that's good enough. And you're totally right, and we'll get there. So spot on, exactly. The reason I'm giving you this strong definition is because, guess what? One-time pad achieves it. And that's going to be one of your, the first homework problem. Okay, to argue that if for any fixed m and m prime, okay, if you encrypt, you choose a random key and you output the encryption of k and m, namely k XOR m, or you choose a random key and you output k XOR m prime, what you get is essentially the uniform distribution. So I'm usually using to denote uniform distribution. What you actually get is uniform distribution over n-bit string. I didn't denote by n, but if m and m prime are n-bit strings, what you get is a uniform distribution on n-bit strings. But I'm going to leave this for you for a homework exercise. So one-time pad actually achieves this definition. So great, wow. So I even got you're totally right that a weaker definition seems to suffice, because why do it exactly the same? But look, it achieves it. So you should be happy. But as you guys already noticed, because you're really on ball, I'm really excited, to teach you. It's only one time. So the comment I got before, so I don't know names because I don't see you guys, I see very few on the screen here. But the comment where we started was like, wait, what if you get encryption not only of m and m prime, but m1 and m2, and m1 prime and m2 prime? You want still some secrecy. And does the one-time pad offer that? And the answer is no. It does not offer that. So let's see what happens if we use the same key for two different messages. Okay, so let's say we shared key. I am not behaving according to the rules of the one-time pad, and I'm using it twice. So first I'm sending you C1, which is the key XOR with M1, and then I'm sending you C2, which is the key XOR with M2. Now, the eavesdropper, she sees C1 and C2. What can she learn? For example, what she can do is she can XOR C1 and C2. And then what is the XOR C1, C2? It's C1 is just the key XORed with the first message. The ciphertext 2 is the key XORed with the second message. And now by transitivity and you can reorder terms, you can get this is just K XOR K, XOR M1 XOR M2, the K XOR K canceled, 0, and you get M1 XOR M2. So actually you learn the XOR of the two messages. You learn something. Now you can say, well, if Eve doesn't know anything about M1 and M2, man, she learned XOR, that's probably meaningless, maybe not a big deal. But actually this is terrible. And the reason why this is terrible is because the real problem is not that she learned the XOR. The real problem is that Eve may have prior information about M1, about part of M1. If she has, let's say Eve knows the header. Okay, so she knows the first part of M1. Then C1 really reveals the first part of the key. So now we've learned the first part of the key. And then if you use the same key without a header, but actually with secret information on top, you're doomed. Now because she knows the first part of the key. So whatever you use the first part of the key for, It's nothing that Eve can decrypt. And that's a serious problem. And actually, often, because like if you actually encode it using ASCII, usually often because you have a lot of information about kind of the distribution of the messages and about certain bits of the message, then actually you do learn information about the key, and eventually you can learn both the messages. It's actually very insecure. And it was actually done in World War II. So this is called the Project Venona. You can Google it. It's actually very interesting, where in World War II, the United States were able to decipher the messages from the Soviet Union because they made a mistake of the way they generated their key. There were repetitions in the key. And they were smart enough to know they shouldn't use one-time pad more than once. But the way they generated the key was not kind of random enough. And there were enough repetitions that it will allowed the US to decipher it, because they essentially used the same key more than once. So this really relies on the fact that the key is truly random and used once. And that's a problem because, you know, we want to use the encryption more than once. Okay. Any questions? So now we're going to move to many time. But I hope, oh, yes.
So here, like, you're like assuming, like, I'm kind of trying to wrap my head around this, but like Eve kind of has, like, obviously they don't actually have the knowledge, but like they're applying the XOR operation to C1 and C2. So that kind of like, what might motivate Eve to do that if they don't know what encryption scheme is being used on the string?
Okay, so first of all, they do know, Eve does know that what's used is the one-time pad. Okay, we always assume, by the way, let me clarify this because I didn't, so that's a good point. We always assume that the scheme itself is not hidden. What's hidden is only the key. And the reason we assume that because in reality, we all know what schemes are used. It's very hard to, like, not assuming you don't know what scheme is used is almost like security by obscurity. You know, usually what we want to say is the algorithms are known. What's unknown is the key used inside the algorithm. Because otherwise, if now the algorithm is known, what do you do? Now you have no encryption scheme. So you need to come up with a new encryption scheme. How would you do that? You know, whereas if the key is leaked, oh, you just generate a new key. So first, we always assume that the adversaries know the scheme we're using. Okay, and in reality, often they do know. For example, today, you know, we use AES. When you use it, we all know it's like public. You know, the schemes we use are all public. That's not a secret. What is secret is our secret keys. So for example, what you're saying, which XOR? For example, the reason why she would XOR is maybe actually she knows some part of M1. Let's say the first, you know, 10 bits of M1, and she does not know the first 10 bits of M2. By XORing, she can learn the first 10 bits of M2 because she knows this, she knows the first, you know, 10 bits here. And so by XORing it with M1, she will learn M2. So that's an example why she would XOR. But as I said, really the danger here is that if the danger is that if Eve knows some information about M1 or M2, then that part of the key that was used to send that information is completely known. Because you'll just XOR that part with M1, you'll get the key. And now that part of the key can never be used again. Because if it does, it's known, so you can decrypt. So that's really the heart of the matter here.
Do we also assume that keys are only like tested once? So like if I'm Eve and I get a message, do we assume that like that there's some limit on the number of guesses I have to like what the key might be when trying to decrypt the message?
That's a very, very good question. So what we're assuming here, you can guess as much as you want, but you don't get feedback. In other words, you know, you can guess, but nobody's telling you if you guess correctly or not. So, you know, but you're totally right that in reality, actually, I love the way you guys are thinking. You guys are really good cryptographers. In reality, you can actually maybe get this feedback somehow. For example, you know, if I see you sending a message, and I want to know if the person, let's say you get a message back, and I want to know if it's 0 or 0 or 1. I can kind of, let's say I guess that it's, I can kind of, in many ways, intercept or send it to you in a way that I can kind of get a sense if my guess was right. It's a bit in public key setting that comes where, okay, let me think. Yeah, so let me give you an example. For example, suppose someone send you K XOR a message N. And I think the message was I love you. Okay, but I'm not 100% sure. So what I'm going to do is I can change the love. I can mull with the message essentially. For example, by changing the love to hate. Now, how will I change the love to hate? The way I would change it is like I'll XOR it with love XOR hate. Think of love and XOR hate as like binaries. Okay, so I think you got a message, I love you. I'm gonna XOR the love part with love XOR hate. Now what happens? You got hate. And now I can see either you're sending a huge message, all rage, like I can't believe you hate me, blah, 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 blah. Or I can see you're like, what? Because if what you got there was not like I can, or let's say if you got love, then you send a very long message, you got hate, you just screw you. Now by XORing that I can see, did you send a long message? Did you send a short message? And I can kind of learn if my message was correct, my guess was correct. So actually in many cases, if you can get feedback in these kind of adversarial way, you know, to your guess. But here I'm not even going there. That's a more, so what the definition I'm showing you now, is what's called semantic security. A stronger definition is what's called CCA, which is a security against chosen ciphertext attack. This is kind of very advanced, like quite advanced topics in cryptography that I'm not telling you about, but it's kind of against like even more secure against an adversary that gets kind of feedback to his guesses in a sense. So, but yeah, for now we're just assuming semantic security.
Okay, that makes sense.
But that's a very good point. Okay, so with that, unless you have other questions, let me go to many times, which is what we really want. We don't want a scheme that we can use only once. What we really want is a scheme that we can use over and over again. And the natural definition is the following. You know, let's just try to make it, you know, exactly as was proposed in the beginning of the lecture. What you really want to say is, okay, for every L, let's say I want to use it for L messages, but for every L, it doesn't matter how many times I'm using it. So for any L, for any number of messages L, and for every actual messages, M1 up to ML, and M1 prime up to ML prime, let's say all the same message for simplicity. So from now on, all the messages are linked to N, as I said. What I want is that the distribution the adversary sees. So in one case, I sample a key and I give him the encryption of M1 up to ML with this key. In the other case, I sample a key and I give him a distribution of M1 prime up to ML prime with this key. And what I want to say, it looks the same to him. He can't distinguish. Or it's the same distribution. So I want to say the distribution on top here and the distribution on bottom here are the same. And then good, it's very secure. And indeed, it's very secure. It's so secure. It's amazing. So you know what the problem with this is? Any guesses for the problem? Okay, let me tell you, it's too amazing. It just doesn't exist. It's too much to ask for. And I don't want to give you a proof for why it doesn't exist, but let me give you an intuition for why it doesn't exist. For example, suppose in one case on top here, M1 of the ML are just zeros. There's zero message. So I encrypt here 0, 0, 0, 0, 0. Okay, so what I'm getting here, oh, okay, sorry, this is a very easy example why it doesn't exist. Okay, one example for why it doesn't exist is, you know, here, if M1 and M2 are the same, what you'll get here is the same message, the same encryption. You'll get encryption of 0 and encryption of 0. Here, if you have different messages, you'll get different encryptions. So you can, you know, now you can distinguish. Okay, so that's one reason why there's no way you could use this definition. But let me actually.
Sorry, I have a question.
Mhm.
What if all MIs are distinct?
Okay, good. What if all the MIs are distinct? Still, there's a problem.
And why then?
Good. Why? So let me give you the, again, it's not going to be a proof, but let me try to give you an intuition. Okay. So now think about them as are distinct. And here's intuitively the problem. So suppose here they're all distinct, but it's just 1, 2, 3 up to L with padding. Okay. So they're all blanked out, but think of in the top here, they're fixed messages, just fixed. Okay. 1, 2, 3 up to L. Now, suppose in the bottom here, these are random. It's like the randomly distributed messages. Or if you want them to be totally distinct, think of the message space as very large. This is randomly sampled from the first part. The second is randomly sampled from the second part, and so on and so forth. Okay, so this is randomly sampled where the first log L bits are 0. This is randomly sampled where the first log L bits are 0, 0, 0, 0, 1, and so on and so forth. Now, they should still have the same distribution, because no matter what they are, they should have the same distribution. But I want to argue that this distribution only has n bits of entropy. Like this, the n's here are fixed. So the only entropy comes from k. So the distribution on top here has only k bits of entropy. Again, this is not a proof that I'm not defining entropy, and I don't want to define entropy. But the intuitive notion is k bits of uncertainty, you know, randomness that came into the picture. Whereas here, you have much more than k bits of entropy, because the messages themselves bring entropy to the picture. So if the messages have entropy in them, then of course it's not the same distribution. Another way to look at it is just to say, look, if the m's are fixed, each ciphertext gives some information about the key. And if you give too many of them, eventually, like, the key is kind of leaked, and then you know the messages. And that's why it can't be the same.
Thanks.
Okay. Okay, but I want to say one more thing here.
I have a question.
Yes.
The problem is that the distribution of MIs themselves, I mean, if both M's and M primes are distributed in a similar way, we still have the problem, or we're talking about randomness of M's?
No, it's actually, even if they're fixed and distributed the same way, even if, well, okay, if they're distributed the exact same way, then it's the same, because, you know, if M1 up to ML are random, just random, and M1 prime up to ML prime are random, you know, if we think of the M's as distributions themselves, then of course it's the same, because it's just, you can exchange M and M prime. If they're the same message or the same distribution, then of course it's the same. Because M and M prime are the same. But even if they're not distributions, even if M1s are like, M1 up to ML is like 1, 2, 3 up to L, and the primes are like L plus 1 up to 2L, there's still a problem. And the way to see the problem is think of L as very, very large, much bigger than the number of bits of K. And then the intuition is that every time I give you an encryption for M1, so suppose the adversary knows M1 up to ML. Every time the adversary gets a ciphertext, that ciphertext contains some information about the key K. And for example, with one-time pad, if he knows M, the ciphertext contains all the information about the key, because you just take the ciphertext XOR with M, you'll get back the key. But even if you're not using the one-time pad, every time you encrypt key with a known message, this is a function of the key. So it gives you some information about the key. And the more such functions you give the adversary, the more information he has about the key. Eventually, this ciphertext, all the ciphertexts have all the information about the key. And at that point, these two distributions cannot be the same. Because if there's all the information about the key, then there's also all the information, then you can see the end, then there's all the information about the ends, because once you have the key, you can decrypt. And then it's on the same distribution. So all of this, all of what I'm saying now heavily relies, and it goes back to the points you guys made again earlier, it's the fact that I'm really asking, it must be the same distribution. Okay, I'm insisting that the distribution at the top and the distribution at the bottom are the same. That we cannot get. But now one can say, why say
question.
Why? Yes.
I'm sorry. Is this L, like, is the top and bottom L different distributions? Or like L distributions, or are they collectively one distribution for the top and one for the bottom?
Okay, so first it's the same L for both, and I'm thinking of it as one distribution. This is one distribution, which consists of L ciphertext, and here I have another distribution that consists of L ciphertext.
Okay, perfect.
Yeah, and I wanna, and here I require that they're just the same distribution. So the L ciphertext on top are distributed identically to the L ciphertext in the bottom. And that's impossible to get. And now one can say, okay, but maybe why it required the same distribution? I mean, not one, you guys said that. So you yourself, like, already in the beginning, like, whoa, that seems like a pretty strong, thing to ask for. And my answer was like, yeah, the one-time pad satisfies it, so you should be happy. But now it comes to haunt me, and you see, told ya, no, we're not happy because the one-time pad satisfies it for one. You need it for many times. And now the one-time pad doesn't satisfy it. And actually, I'm telling you, nothing satisfies it. So now you're like, wait, so we didn't like that definition to begin with, and you were right. Okay, so what is the definition? Sorry. Good. So, but let me tell you, you shouldn't like the definition, but suppose for a second that I could take my little key K and I can somehow magically, now here's the magic, I can make it a large, like from n bits of randomness, I can make n times L bits of randomness. Now, of course I can't just generate entropy from nothing, that's impossible. But suppose for a second, let's go to dreamland, and suppose there was a way to take n bits of randomness and make n times L bits of randomness out of it. If you could, we would be done. If you had, so just suppose for a second, you had a function that allowed you to generate more and more randomness. So you take the function on your secret key K, oh, sorry, this should be n bits. This is a typo, because we always use n for our message length. So suppose I took an f, I had some function f that took your key, and you applied it to 1, you get a uniform U1 uniform over n bits. You apply 2, you get another uniform. You apply 3 up to as many as you want for every n, or what we denoted before by L. Sorry, I changed notations on you. But as many times as you want, you can get more and more random strings. So all this, think of this as like all this together is uniform over 0, 1 to the n times message length. Suppose I had this function. You apply it on 1, you get randomness. You apply it on 2, more randomness. On 3, more randomness. And all these randomness together are just like a huge random string. If you had that, it would be amazing. Because now you can use this as a pad to encrypt the ith message. So the first message, you use SK1 as the pad. It's uniform. So you just use a one-time pad. You take this string, you XOR it with a message. Now you want to encrypt again. Oh, you can't use this pad anymore. That's done. Use this pad. You use that pad to encrypt the second message. Now you can't use this anymore. Use the next one. And the point is because all of this is completely random. Even if you learned U1, U2 is still random. So you can use it. And even if you knew U1 and U2, you used it and everything was discovered and everything. Still, U3 is still random, so you can use it. So if only we could generate this randomness, we could use the one-time pad over and over. I mean, we can just make a many-time pad version in this way, and then we would be done. So then we had a many-time secure encryption scheme and we're done. Okay, that's very nice. But at this point, you should be like, okay, that's very nice, but I'm really in dreamland. So let me fix this typo again. This was the N, small n. So I'm like, if, but we know we can't do that. So what's, you know, and indeed, we don't even have a many-time secure encryption, so forget it. But now comes the magic. And this is one thing, you know, I want to teach you about cryptography, is that, you know, if you think about cryptography, everything we try to do is impossible. And the entire kind of field of cryptography is an art of kind of overcoming impossibility results. So now we hit a wall of impossibility. Now the question is, how do we go around the impossibility result? And the main insight here is the following. Indeed, we cannot generate true randomness. But actually, we don't really need a true randomness. It's enough to generate something that looks random. It doesn't need to be really random. It's enough that it looks random. Because if from her perspective, it looks random, it's good enough. And actually, generating things that look random, that's actually possible. And let me add, you know, that should not come for you in a big surprise. Because, for example, we do this all the time. You know, when we toss a coin, it's not random. If you knew the laws of physics and you can calculate, you know, all the positions and so on and so forth, you would know if it's a head or a tail. But we can't calculate that. So from our perspective, it's a random, we call it a random coin toss. Nothing about it is random. It's just computational randomness. Okay, so we see computational randomness when we roll a dice. We think the outcome is random. It's not random, but you know, it's close enough. From our perspective, as kind of human beings, as muggles, it's random. So that's all we need. We need randomness for muggles. Okay, or for kind of, you know, polynomially bounded adversaries. Okay. Yes.
What can we call as true randomness? Is there such a real-life example, of true randomness?
Good. So you're asking, do we at all have true randomness? Is your question?
Yes.
Yeah, great. So actually, the answer is we do have true randomness. I think the way we know how to generate true randomness is using quantum. So there are quantum chips now that are generated that we believe, you know, if we believe the laws of quantum mechanics, then they generate true randomness. But from what I know, that's the only way we really know how to generate true randomness. And let me actually say, you know, encryption schemes really rely on randomness. We'll talk about it more, but already you see that it's very important that the key is random. If the key is known, we're dead. So, you know, randomness is paramount to cryptography. And actually generating randomness, I kind of assume, you know, forget about how you share it secretly. How do you even get randomness to get the key? That's another question. Forget about just meeting and sharing it. How do we even, you know, how do we generate this randomness? And a lot of the attacks in cryptographic systems are exactly on this part, that we're not very good at it, at generating randomness. And a lot of the time, the way we generate randomness, well, they have so many ways. like based on keystrokes, timing, a lot of kind of these things. But we've seen, for example, there was really beautiful work by Nadia Henninger and a bunch of others. I don't remember the set of authors, but they showed attack on Bitcoins where they showed that people, they had like RSA keys, and RSA keys are just kind of product of two primes. But they showed people used the same primes. Why did they use the same primes? Because they didn't have, they used kind of the same randomness. And the same randomness generated the same primes. And then like they noticed so many people share kind of, their keys are not independent because they use similar randomness to generate the keys. So actually generating randomness is a huge problem. And I think now more and more we're leaning on quantum to do it for us. I don't know how much it's deployed yet, but it's definitely the way kind of things are going, is to use quantum to get good randomness, because that's one thing that we know how to kind of believe gives you true randomness.
That just reminded me of something. Was there a similar attack against SSH about 10 years ago?
Yeah,
where people's public keys had the same issue?
There's a lot of, yes, there's a lot of attacks because of bad randomness. That's a very common way to attack schemes. So yeah, there was an attack on SSH. Yeah, probably, yeah. I don't remember exact 10 years, but yeah, something like that. Yes. Okay. So, but good news, we don't really, at least now, for, to get many time pan, we don't need true randomness. We need computational randomness. And what do I mean by computational randomness? What I want is, let's say we do share a key K. Again, calling this to the N. What I want given, so I do assume that K here is random, completely random, and I'm not gonna, go into the details of how this is done. I'm just assuming we have some quantum chip that generates randomness for us. And now suppose I give you a deterministic function. So some fixed function that if you take the key and apply it on 1 and 2 and 3 up to n, you really, really get randomness, like fresh randomness. And so so you don't get something that is truly random, but you see it's a bit curvy, almost random. And what I mean by almost random, I mean it's computationally indistinguishable from random. So what does computationally indistinguishable mean? So I don't want to go into complexity theory too much, but usually we think of efficient machines are polynomial time, or what's called polynomial time. And we assume our adversaries are polynomial time. Okay, so we assume of course, in practice, this polynomial time is replaced with, 2 to the 128. So any adversary can run at most 2 to the 128 steps. But in theory, we use usually polynomial time. And then we want to say that from the I, for any polynomial time adversary, if he gets this distribution or this distribution, he cannot tell the difference. So he tries to guess. Okay, let's say I tell him, output 0, I'm going to give you either this or this. If it's pseudo-random, output 0. If it is random, output 1. Then what I want to say, this is computation distinguishable if the probability of the adversary guessing correctly is at most half. Of course, he can guess probability half, but he cannot do much better than that. So that means computation distinguishable. So without the formalism, because that's not important, what's important here is computation distinguishable means from the eye of an actual adversary, it looks the same. It's like coin tossing or rolling a dice. It's not random, but for us, it looks random, and that's good enough. Okay, so if we could do that, we would be done. The question is, how do we generate computational randomness? I mean, what is this function? Okay, so good. So here again, the main insight here is what we're going to do is we're going to use hardness to generate computational randomness. And again, this is simple to the rolling a dice. The reason that it looks random is because it's hard to do the calculation to understand the output. Or the reason that coin tossing looks random is because it's hard to calculate the actual answer. You can calculate it, It's calculatable. It's just very hard. So similarly, we're also going to use hardness to generate randomness. And now I'm going to show you though how we use it here, because we're not going to use the laws of physics. There's not going to be any coin tossing or die rolling. So what we use is what's called a one-way function. So let me tell you what a one-way function is. A one-way function, think of it as a function from n bits to n bits, okay, that is easy to compute. So computing it forward is very easy. Given x, it's easy to compute f of x. But given an element in the range, y, it's hard to invert. It's hard to find x so that f of x is y. Okay, an example, for example, if you have two primes, multiplying primes is easy. But given a big number of the form p times q, we believe that factoring it is hard. So finding p and q is hard. That's called factoring problem. That's just one example. But we have many examples of one-way functions. Okay, why am I going, now I'll say all you need is a one-way function. Oh, one-way function is great. Why? Well, because you have the hardness here. But you say, okay, but how will I use the hardness? Well, remember I promised you big F, so the big F of I'm key of 1, key of 2, key of 3 is all random. Well, how do I get that? And so here's how I'm going to get it. First, let me, instead of using F of any function, let me use a permutation, meaning it's 1-to-1 and onto. Okay? Or in other words, what I mean by permutation, if you take a uniform distribution over 0, 1 to the n and apply F on it, you get a uniform distribution. Okay, we also have one-way permutations. Okay, so it's a one-way, but it's also a permutation. Now, if you have a one-way permutation, we're almost there, because what I can do, okay, actually, what I can do, I can now, so you know what, let me just try to output just one more bit. Okay, let me take a key of length small n and generate randomness of size n plus 1. Just one bit of randomness I'll generate for you. Okay, and actually in the homework assignment, you'll generate more. But let me first get one bit of randomness. What is the bit of randomness? Well, you know, ideally what I would want to do is, let me give you kind of an attempt. How about this? I'll give you f of u, that's random, that's n bits of, so sorry, what is big F? I'm going to take big F, actually, well, we're going to call it G for generator, okay? I'm going to take n bits of randomness, this is of length n, and I'm going to generate n plus 1 bits. Here's my n plus 1 bits. First, I'm going to output f of u, that's n bits. Now, I just gonna need one more bit. Now, it's very tempted to say, okay, let me call this, instead of u, let me call it x. So I have this n bit x. It's uniform though. I'm going to output f of x. Now I know that from f of x, it's hard to compute x. So I have hardness there. But what do I do with it? You know what? Suppose I knew that the first bit of x is hard, really hard. So if you see f of x, you don't know the first bit of x. The first bit of x looks random to you. Then great, then I'm going to output f of x and x1. And if it's the case that given f of x, x1 looks random, it's so hard to find x1, then you're done. I generated a bit of randomness. Wonderful. So all I need is to find this one bit hardness in x. Now I know, look, you cannot find all of x. There must be some hard bit there. So what is the hard bit? As long as I can find that hard bit, I generated randomness. And when I mean hard bit, I mean a bit that given f of x, you cannot guess that bit was probability better than half. If I have that hard bit, I'm done. Okay, so this is exactly what's called a hardcore predicate. A hardcore predicate is said that if a hardcore predicate of a one-way function, f, is the following. It says, look, if you take a random x, f of x is random. sorry, if you take a random x and you look at f of x, you cannot find the entire x. There must be one bit of x that's really hard. I'm going to call it the hardcore predicate. And a hardcore predicate is exactly that bit, that if you see f of x, this bit looks uniform. This is uniform over one bit. It's just one bit, one random bit. So of course, it's not really random. You can, invert f, work really, really hard, invert f, find x, and compute p of x. P of x is not really random. These are not the same distributions. But computationally, because f of x is hard to invert, you can invert it. It just takes a lot of time. And because from your perspective, you can't find x, there must exist one bit of hardness, which is the hardcore predicate. And if there exists this one bit of hardness, we're good.
So do you think we could get like some examples of maybe a one-way function and its predicate? Is it easy to construct these? Like, is there a simple one you know of?
Yeah, so one example, okay, the example I have, first of all, they're not very easy. One example of one-way function is that product of prime example. So one example of f is take like a set of all primes. Oh, wow, this is really bad. Set of all primes times set of all primes to, the natural numbers. And what it does, it takes P and Q and it outputs P times Q. Okay, the reason I don't love giving this example is because it's hard to think of it as a function goes from 0, 1 to the n because it's only the primes, and if it's completely random and you multiply, sometimes it's easy to factor. But as a close proximity, that's what you should think of. But now you can ask, so what's the hardcore predicate? By the way, there's also things under group theory, which you'll have one of them in the homework problem. But I'm going to leave it because it involves some algebra, and I think I'm afraid I'm going to lose too many of you once I add this algebra. But there are other examples. So we'll see another example in the homework. But then you can ask, what's the hardcore predicate? And actually, you can also ask, okay, we saw one example right here of a one-way function. But for A, I want to see an example of a one-way predicate. And B, how do we know that we have a one-way predicate? Okay, maybe you cannot find all of x, but there's no one bit that's hard. Maybe each bit is 0.99 hard. Like you can't guess with probability better 0.99. And then together it's hard, but there's no one bit of hardness. And we give like one bit that's hard to guess with probability better than half, like really like random. Who says there exists such a one? So you had a great question. You said you're essentially right to say, wait, how do I know that it exists? First of all, how do I know the one-way functions exist? Okay, and actually we don't know that they exist. Even the example I said with product of two primes, we believe it's hard to factor, but it may be easy. That's an assumption. We believe it's hard to factor. We don't actually know that. Okay, but let's assume it's hard. Still, do we have a hardcore predicate? Who says we have a hardcore predicate? So that's a very beautiful theorem of Godach and Levin that says that indeed every one-way function does have a hardcore predicate. And the example, if you want to see the example of a hardcore predicate, actually the example they give, they show for every one-way function f, it has a hardcore predicate p, but their predicate is a randomized predicate. So the predicate, they have like randomness r. So essentially their predicate takes x, but also randomness r, and it outputs the sum of xi times ri mod 2. And what they claim is, what they show, is if for a random r, you can guess this with probability better than half, then you can actually find x. So it may be that for many r's you can find it, but with some probability. But for random r, it should. So maybe for r, which is 1, 0, 0, 0, which is kind of x1, maybe it's easy. So there may be many kind of particular r's for which this is easy, but for a random r, this should be hard. So they gave a construction of a randomized hardcore predicate. Actually, coming up with a deterministic one is not very easy. I think that we do know of some specific hardcore predicates for like the factorization, but it's not, I don't have it off the top of my head, and it's not very easy to state, because even the example of the product of two primes, just defining the range and the image, it's a bit tricky. But this is a hardcore predicate for any F, but it's a randomized hardcore predicate. But let's leave the details alone for a second. And suppose you believe that there's a predicate. Okay, every one-way function has a predicate. Then we can essentially, what we can do, we can use this one-way permutation with the hardcore predicate to generate randomness. We just generated randomness. It looks like n+1 bits of randomness. So we generated a bit of randomness. That's amazing. So here's our randomness generator, G for generator, on input X. It outputs f of X and the hardcore predicate on X. And this is n+1 bits, they look random. You know, I told you that the predicate has randomness. So actually the way it really goes is you give X and R, and you output R, f of X, and P of X with R. So the hardcore predicate is hardcore even if you know R, okay? So now the input is X and R, so it's 2n bits, and it outputs n bits, which is R, n bits, which is f of X, and the hardcore predicate. So it outputs 2n+1 bits. So the point is you generated one more bit. Okay, but I'm going to leave the point of the randomness alone because I think it's kind of more details and I want to give you more of a high level idea. So forget about the fact that, yeah, unfortunately, we don't have a deterministic hardcore predicate. We need randomness, but let me abstract that aside. The point is we managed to use hardness to generate this randomness. And now I got one more bit of randomness out of it. That's it. So what we really need is to generate many bits of randomness, not one. I showed you G that takes n to n+1. What you want is n to n plus as many big N as I want. And then I can use it to do many one-time pads. So that's going to be a homework assignment for you, how to go from, if I give you what's called a pseudo-random generator, this is called pseudo-random generator because it generates pseudo-randomness. So if I give you a pseudo-random generator that generates one extra bit of randomness, you're going to come up with a pseudo-random generator that generates big N bits of randomness. And then you have one, and then you're done. You can use it for many times. Questions? So let me just say, let me actually end by saying the following. Forget it. So yeah, so what I showed you is this pseudo-random generator. Actually, what we really use is what's called a pseudo-random function. I'm not going to go into at all how to construct that from a pseudo-random generator, but there's a way of doing that using some tree construction, which I don't want to get into. But a pseudo-random function is a function that takes two pairs of n bits and output, it can be 0, 1, can be n, whatever, it doesn't matter. It can be here anything. And such that for for a random key k and any distinct exon of the xn, if you apply the function on x1 and x2 up to xn, as long as they're distinct, they all look uniform together. This joint distribution is like uniform over n times n bits. And now, if you have such a thing, all you need is a pseudo-random generator to generate it. Now here's my encryption. And this is the symmetric encryption that's used all over the place. Okay, every time, this is the most useful encryption scheme. So, you know, that you actually use it on a day-to-day basis. And it's the following. The way you encrypt them, so you want to use this kind of randomness generator and apply a one-time pad to it. And the way you're going to do it is you're going to, but the question is with what are you going to use it? FK with 1, with 2, with 3, which one? Which kind of which X are you going to put here? And the way it's done in practice is they say, let's use random R. So you choose a random R. You can also have it kind of a sequential. You know, the first message use R1, the second message R2, the second like 1, 2, 3, and so on and so forth. But then you always need to keep state of what you're using and so on. So instead, what you can do is every time I want to send you a message, I'm going to choose a random R. I'm going to send it to you. And then I'm going to pad my secret message with FK and R. So this pad. And because R is large, it's like in 0, 1 to the n. Unless I use it many, many times, I won't use, every time I choose a random R, there won't be collisions. If n is big enough, like, you know, I know 256 bits or something like that, I can generate many, many, many R's. The probability that I'll generate the same R twice is very, very small. And then that's going to be my encryption. Okay, so I send you the R. I pad the message, which is FKR. The adversary knows the R. He knows the R. That's not secret. But he does not know the K. The K is what he does not know. So even if he sees many, many, many R's, okay, so he sees many X's, if you will, still all the pads together, they look random. So they're all good pads as long as they're distinct. Okay, questions?
Sorry, I have a question. Can you move back to the previous slide? Sorry. Here we use the what was it? The hardcore predicate.
Yes.
To expand our random from n-bit string to n+1 bit string, right?
Precisely.
And yeah, and from here, from my point of view, it adds some kind of unrandomness to the whole generated random string. But since we can't compute the hardcore predicate, it's negligible, and we just say, okay, the n+1 bit string is true random,
yes.
or
Looks
true
like
pseudo-random.
Exactly.
Okay. But here's my question: if we try to do this, I mean, for like m times after this, and we use the n-bit message to get a n+m bit message, is this also a negligible unrandomness, or it would be wrong to use this method?
Okay,
I mean,
that's exactly that's a great question. That's actually.
Oh,
sorry, go ahead.
Sorry. I was just saying, if we use it many times, one after another, and we expand the random message we are trying to achieve, would it still be random or not? Sorry.
Good. So the answer is, okay, the question is how to do it, how to expand it more and more. That's the homework assignment. But the answer is, yes, it will still be pseudo-random. And essentially the reason, intuitively, the reason it will be pseudo-random is because if you have a bunch of things, if you have like, if X, let's say, is indistinguishable from Y, and Y is indistinguishable from Z, and Z is indistinguishable from W, then X is indistinguishable from W. So as long as you do this at most polynomially many times, the indistinguishability remains. It's transitive in that way. So the short answer is yes, it will still be pseudo-random as long as you add only polynomially many bits. You can't add too many. You need to add polynomially many. But in reality, it stays pseudo-random.
Okay, thanks.
Yeah. Look, all these things are very, I essentially gave you a crash course in cryptography in one lecture. So, And I'm out of time. But I just want to add one more thing. The last thing I want to comment is note that the encryption scheme I ended with uses randomness. It's a randomized scheme. So the encryption, I forgot to put here, K. So it takes as input the key, the message, but also it takes as input randomness. And actually, it's very important to have randomness because exactly what we noticed before, that without randomness, if you encrypt the same bit twice, you'll see that it's the same bit because it's deterministic. And you don't want to know that you encrypt the same bit, the same message twice. For example, if I encrypt no, you know, you want to go no. Eventually, the person will know that what's there is a no. If he sees the same thing over and over and over again, he'll start learning things, right? He'll start learning that every morning, you know, I say, hey, do you want breakfast? Yes, yes. Oh, this is yes. And then maybe later I'd say, oh, do you want to go to work? Yes. So these things at first we can learn. So the point is, if you really want this type of semantic security for every, even for non-distinct ones, which is really what we want, we need to have randomized schemes. And our schemes do have randomness. Okay, so I'm not going to go over the homework because I don't have time, but I hope you'll enjoy it. And thank you very, very much. And tomorrow we'll kind of go over another very magical aspect and beautiful aspect of cryptography, which is your knowledge boost. So thank you. And I also want to say thank you so much for your questions, guys. That was really, really great. I really enjoyed teaching you. You're promising cryptographers.